This is a classic percent dissociation problem regarding acids. They're giving us 3 different acids with varying strengths, and they're asking us to calculate percent dissociation given that you start with a 0.40 molar concentration of each of the acids. Part A is actually an easy one. Nitric acid, HNO3, is one of the 7 strong acids. Hopefully you would recognize that as such. What that means is strong acids dissociate completely. That is, 100% of the nitric acid molecules that enter solution will break apart. If you wanted to show some calculation for this, which you wouldn't necessarily need to do, you would say, okay, percent dissociation is always the concentration of hydrogen ion at equilibrium over the initial acid concentration. And you multiply by 100 to make it a percentage. Well, in the case of the nitric acid problem, part A, the initial acid concentration of 0.4 matches the equilibrium concentration of hydrogen ion. So 0.4 over 0.4 times 100% would be 100. For the other 2 parts, part B and C, we have weak acids. We'll have to make an ice table for each of those. Let's start with part B, nitrous acid, HNO2, which is not one of the 7 strong acids. We'll write a good dissociation equation, and we'll make an ice table. The initial concentration of the acid was given as 0.4. You can safely assume that the other species have concentrations of 0. We shift to the side with the zeros without even having to calculate Q. So plus is on the right side and a minus on the left side. All of the species in this equation have a coefficient of 1. So it's minus 1x plus 1x and plus 1x, which gives us equilibrium expressions as written in the equilibrium line of the ice table. The Ka expression for this equation would be hydrogen ion times nitrate ion concentration all over the original acid concentration. We've got to find x in the ice table. Well, we plug in x times x all over the expression 0.4 minus x. We can safely assume that 0.4 minus x is roughly equal to 0.4. And if we can do that, then the equation becomes a lot easier to solve. Okay, so if the Ka value was given to us, we've got to look up into the table 14.2, locate nitrous acids, and find that its Ka value is 4 times 10 to the negative 4th. And we'll multiply both sides by 0.4 and take the square root of that, and we get a value of x of 0.0127. Percent dissociation then can be found by taking the concentration of the hydrogen ion at equilibrium all divided by the initial acid concentration and multiplying by 100 to make it a percentage. So we've got the value of x in the ice table of 0.0127 gives us the equilibrium concentration of hydrogen ion of 0.0127. The initial acid concentration was 0.4. And if we crunch the numbers, this one works out to be 3.16% dissociated. In part C, we're dealing with another weak acid. This time it's called phenol. And if you look on table 14.2, it's the very last one listed with a Ka value of 1.6 times 10 to the negative 10th, a really, really small K value. We'll follow the same procedure that we did in part B. Start with a good dissociation equation. We'll plug in the initial concentration of the acid. Throughout this problem, that initial concentration, they told us, was 0.4. And you'll notice, students, the ice table for part C is exactly the same as the ice table for part B. It's just for a different dissociation. We'll plug in the values that we got for X from the ice table. And we'll go ahead and make the mathematical assumption that 0.4 minus X is roughly equal to 0.4. So long as the percent dissociation works out to a number less than 5%, we're safe to do that. And I can tell you, based on the size of this Ka value, in the order of 10 to the minus 10th, we're definitely going to be safe in making the mathematical assumption. So I'll take that teeny tiny Ka value times 0.4 and take the square root of it, and X works out to be, in this case, 8 times 10 to the negative 6th. Once we've got that value of X, we have the hydrogen ion concentration at equilibrium. Based on our ice table, we know that X is the concentration of hydrogen ion. So we can plug into the percent dissociation equation, which would be the concentration of hydrogen at equilibrium all over the initial acid concentration times 100. And in this case, it works out to be a very, very small 0.002%. In part D, they ask us, how is the percent dissociation of an acid related to the Ka value of that acid? And importantly, they say in that part, assuming equal initial concentrations of the acid. So we're not comparing scenarios where you have different initial concentrations. Well, if we just quickly list the Ka values for each of these acids, for phenol it was 1.6 times 10 to the negative 10th, and we got a percent dissociation of 0.002. For nitrous acid, it was 4 times 10 to the negative 4th, and we got a percent dissociation of 3.16%. And for nitric acid, the strong acid, the Ka value, as with any strong acid, is something that approaches infinity. So in other words, it's really, really big. Well, you tell me, what's the trend? Really big Ka value, really big percent dissociation. Medium Ka value, medium percent dissociation. Really small Ka value, really small percent dissociation. So the trend is As percent dissociation goes up, Ka goes up. Or you could conversely say as percent dissociation goes down, Ka goes down. In other words, there is a direct relationship between those two variables.